I want to talk about a measure of dispersion known as the coefficient of variation. Now, you're probably familiar with the standard deviation, which is a measure of dispersion around the mean of a variable. The problem is that the size of the standard deviation depends on the scale of the variables. For example, if you scale up the observations by a factor of x, the standard deviation will be x times larger, even though the observations aren't more spread out around their mean. Now, it may be clearer if we take a look at an example. Suppose we have two sets of variables, y and z, and the observations for y are 10 and 20, and the observations for z are 100 and 200. And suppose there's a 50% chance of each one of these observations, the 10 and the 20, or the 100 and the 200, occurring. So the mean of y is 50% times 10 plus 50% times 20, or 15. The mean of z is 50% times 100 plus 50% times 200, which is 150. If we calculate the standard deviation, recall that the standard deviation is the square root of the deviations from the mean squared multiplied by the probability they'll occur. So there's a 50% chance that we get the first observation of 10 minus the mean of 15 squared, plus there's a 15% chance of the second observation of 20 occurring, and the 20 minus 15 squared. So what is this? 10 minus 15 is minus 5 squared is 25. 20 minus 15 is 5 squared is also 25. 50% of 25 is 12 and a half. 50% of 25 is 12 and a half. 12 and a half and 12 and a half is 25. Square root of 25 is 5. I do the same thing for z. 50% chance that you get 100 minus its average or mean value of 150 squared, plus 50% chance that you get 200 minus its mean value of 150 squared. And so what's this? 100 minus 150 is minus 150. If we square it, it's positive 2,500. If we take 200 minus 150, that's positive 150 squared. That's 2,500. 50% of 2,500 is 1,250. And 50% of this 2,500 is also 1,250, right? 1,250 plus 1,250 is 2,500. Take the square root of 2,500 and you get 50. But clearly the dispersion is the same, okay? That these values are spread out the same. 100 to 200 is the same spread as 10 to 20. But the standard deviation of z is 10 times larger than the standard deviation of y because we scaled up these variables by a factor of 10. So how can we deal with that? We'll deal with that by using something known as the coefficient of variation. And the coefficient of variation normalizes the volatility by dividing the standard deviation by the mean. So if we go back to our calculations, the coefficient of variation for y is going to be the standard deviation, which was 5, divided by the mean of y, which is 15. So 5 divided by 15 is 0.333. The coefficient of, the standard deviation of z is 50. The mean of z is 150. So if we take 50 divided by 150, we get a coefficient of variation for z of 0.333. So you can see that they're exactly the same, and we did this by scaling them or by dividing them by the mean values. Now, we can also use this for comparing the risk of two stocks. Suppose the stock A has a mean return of 8% and a standard deviation of 6%. Suppose stock B has a mean return of 16% and a standard deviation of 10%. Well, it appears that stock B has greater dispersion than stock A, but if we look at the coefficient of variation, we see that the coefficient of variation for A, 8% 6% standard deviation divided by the 8% mean gives us a coefficient of variation of 0.75. The coefficient of variation for B is going to be the standard deviation of B, which is 10%, divided by the mean of 16, which is 0.625. So it turns out that even though B has a greater standard deviation, it's actually less spread out around its mean. It's twice as high as the mean of A, although the standard deviation is not twice as big. And the coefficient of variation helps us to understand that. So this may be a better way for comparing the risk of different securities that have different mean returns.